Let's look at something called the intermediate value theorem. The intermediate value theorem. Okay? Sometimes affectionately called in my classroom the IVT. So we're going to kind of discuss this in reverse of maybe my typical approach to something like this. I think it would be useful to sort of build it backwards. So what we're going to do is we're going to start with a graph. So what I recommend is leave some space to write the theorem, and we're going to start with the graph down here, and then as we're building the graph, we'll come back and we'll make statements about the theorem so we can see the relationship of how this thing's built. Okay, so here we go. We're going to, up here we will state the IVT, the intermediate value theorem. We'll state it there, and we'll illustrate it. We'll illustrate it down here. So here's the idea. We're gonna work in the first quadrant. We'll keep it simple. Okay, we'll work in the first quadrant, and let's say that we've got two x values that we're interested in called a and b. Let's call the function that we're graphing here, let's call it f. Let's give it a name. Then if this function f is continuous on the closed interval from a to b, all right, if the function f is continuous on the closed interval from a to b, then that may look something like this. You'd have a closed endpoint at a. You'd have a closed endpoint somewhere over here at b. It doesn't have to be higher, right? It doesn't matter. The point at a could be higher than the point at b. But the function is continuous on the closed interval. So it has to include the endpoints of that interval. And then in between a and b, you could draw any sort of graph you want, but it can't have any breaks or gaps in it because it has to be continuous. Okay, so let's start by writing that in the IVT. If f is continuous on the closed interval from a to b, so we have that. And sort of a subtle piece of the intermediate value theorem is that you don't want the outputs of the endpoints to be the same. So what is the output at this endpoint? Well, if the input's a and the function's f, then this output, we won't be fancy with it. We'll just call it what it is. It's f of a, right? And the output for this input b is f of b. The intermediate value theorem is useless to us if those two outputs are the same. In other words, if you start at this point and you trace the path along and you end up at the same exact y value, you've made zero change vertically. That case is useless to us for the intermediate value theorem. So another assumption that we make here is that, well, the function has to be continuous on the closed interval, and the output at a better not equal the output at b. Because if it does, we can't really make any conclusions along the lines that we're going to want to make. Now, as far as theorems go, these two statements are what we call hypotheses. They're the assumptions that you make. They're the if part of the theorem. If this is true and this is true, comma, then. So we have our two hypotheses. Then we make what's called the conclusion. So if both of these are true, the intermediate value theorem is going to guarantee something for us. So let's see what that is. Let's come back to the graph. The idea of the intermediate value theorem now says, basically what it can do is it can guarantee that all of the y values between f of a and f of b, you can imagine the y values that live there. For example, the y value at the bottom of this trough is not a y value that lives between f of a and f of b. So we're not going to know anything about it. But you could pick any y value between f of a and f of b. The intermediate value theorem guarantees that if you meet these hypotheses, it guarantees that there's some x value in between a and b whose y value will equal the y value that you chose, okay? Now that's a lot to take in. So let's now name some things so we can see what's going on. So let's pick any y value that we want between f of a and f of b and give it a name. So let's say, again, it doesn't matter where it is, but let's say we choose, let's choose this y value here. Let's call it n, okay? No particular reason. So nothing fancy about n other than it's between f of a and f of b, all right? So what the intermediate value theorem says is that then for any n, which is a y value, for any n between f of a and f of b, right? So you can pick any n you want there. For any n between f of a and f of b, what it tells us is it guarantees that there's some x value, that lives between a and b, nowhere else, but it guarantees that there is some x value that lives between a and b, which we can see, the x value here, whose y value is that n. All right? So for any n between f of a and f of b, the way we say this is there exist. So the intermediate value theorem is an existential theorem. It guarantees the existence of something. That's pretty nice. It's not as nice as providing a way to determine the thing that it guarantees to exist, right? So these are types of theorems that as mathematicians, when you're doing research, if you can guarantee that something exists, that's good. The next step is there a process you can elaborate to find it? And that's not what the intermediate value theorem is, okay? Now there may be cases with particular functions and all that where we could figure out what we're looking at. But that's not the point of the intermediate value theorem. So you pick any y value you want. The intermediate value theorem guarantees that there exists an x. So there exists x between a and b. A fancy way to write that is x is an element of the open interval from a to b. That means that x can't equal a and it can't equal b. It has to be between a and b. All right, that's really important. So the original function has to be continuous on the closed interval. Well, one reason that's true is because if these were open circles, you couldn't even refer to f of a and f of b because there would be no outputs. Okay, so the function has to be continuous on the closed interval, and we can find our x in the open interval between a and b. There exists an x in here such that f of x, the output of that x, is the y that we randomly chose. Okay? So we can always find an x that will output the y that we chose. And furthermore, that x will live between a and b. We can always find one that lives there. Okay? So basically, all it's saying is that if your function is continuous on this closed interval, there's no way your function can go from this y value to this y value without hitting every single y value in between. It can't skip any, right? That makes sense. That's what continuous is. There are no gaps in the graph. So the only way you can go from the lower y value to the upper y value is by hitting every single y value here. That's why the choice of n can be arbitrary as long as it's between f of a and f of b.